Good morning, everybody, and welcome back to Next Door NetAdmin. Today we're going to be talking about WAN and SD-WAN. This was a request sent in by Yamanin Niname. That's a wonderful palindrome of a username. But SD-WAN, what is it? Well, it stands for Software-Defined Wide Area Networking. And to talk about this, I want to first do that thing that I always do and go back a little bit and talk about what's the difference? How are we defining the term software-defined networking? So when you're looking at networking equipment, routers and switches primarily, they get the speed that they need in which to operate. They get that mainly from implementation in hardware. And this makes a lot of sense when you think about it. Hardware, if everything is programmed in hardware, then you're basically operating at the speed of the hardware. You're not having to go through a bunch of software instructions to say, okay, first load this value, then do this comparison over here, maybe branch to a different section of code, figure all of this out. If it's just hardware, it's just, I connected to here, so off we go. And because of that, most switches in particular, let's start with switches, they're built with hardware that facilitates that. They have special memory, something called TCAM, which stands for Ternary Content Addressable Memory. And that's a separate topic all on its own, so we won't get too far into that. But the basics of it is, at its most fundamental level, as a packet comes in, the switch receives it, and in hardware looks at the address that it's both coming from and going to, and then has the hardware capability of looking for this address, and as it analyzes that in hardware, it essentially lights up the required destination, if that exists in the switch's memory, and it just goes straight to that port and out onto the wire. Simple as it gets. As you increase the complexity of the switch's configuration, say by adding VLANs, that adds an additional filter essentially into the hardware memory, so that as it's looking that up, it's first parsing the VLAN, and then so that it's selecting only those sections of hardware that have addresses on that VLAN, and then looking up the destination address on that, so that you're always filtering by just the VLAN first and then looking for the hardware address. So this is all done in hardware, which means that your configuration on the software side, in the interface that's running software, that's a separate portion altogether from the basic operation of the switch. And in fact, when you're looking at this, there's two different components that you can talk about. You can talk about the switching engine, which actually works with the hardware to, make sure that things go in various places, or you have the management engine. And the management engine is the programming interface that we, the admins, work with to change the configuration of the switch. And that can essentially reprogram some of the hardware in order to, add additional filters for things like VLANs. But you are reprogramming hardware. The switch does not have to look at every packet going through it with its CPU. And that means that these CPUs can often be much, lower capacity, lower spec. They don't need a lot of power. Most of this is being done in hardware. And that's where the bulk of the cost is this is specialized hardware. This is just how it works. Routers are somewhat similar. Routers have hardware that basically operates on the level of your routing table. So you're storing routes saying where you can find the individual networks that you need to address, and you have a default route as a catch-all if there isn't something else in the table, great. And it tells you what port it has to go out, and that way it can just be routing at speed. But that's just routing. That doesn't cover anything else. And in fact, a good example of this would be my good friend, the Cisco 1920, the 1921 routers. They have gigabit interfaces. They can and are designed to route at gigabit speed, but that's just routing. As soon as you add anything else that isn't in hardware, such as NAT or firewall, anything like that forces packets to go through the CPU. And as soon as you do that, these gigabit interfaces, yes, they can connect and synchronize at gigabit speed, but the traffic going through the CPU, you will top out at about 120 megabit maximum, no faster. Even under laboratory conditions, you're only going to get to like 122. So in real world conditions, 120 is your max, maybe 100 megabit tops. For an internet connection, that used to be pretty darn good, but now we have fiber connections in many places around the globe, and regular consumers, regular offices might have a 500 megabit connection or a 750 megabit connection or gigabit, or 2 gigabit, okay. These routers were never built for that. In hardware, they can do stuff like Cisco Express forwarding. The very first packet has to go through software to, do the analysis of policy and figure out where it's supposed to go. But after that very first packet, all of the switching is done in hardware. All of the routing is done in hardware. You can just make sure that that flow goes from one interface to the other, gigabit speed. But as soon as you have to do NAT and check an address translation and rewrite the packet and recalculate the checksum, all of that's going through a CPU, which is much, much slower. So for the longest time, certainly in traditional networking, everything is done in hardware, and that's your expectation. You're operating at the speed of hardware in order to reduce your latency and make sure that you're not severely impacting the speed of the connection, because users notice that kind of thing. But now we move into the era of software-defined networking. And this is where things kind of reverse. I said most of the cost for traditional switching is in the hardware, because this is all done in hardware to minimize latency and keep speed as fast as you can get it. And the CPU was much lower spec. Okay, but what if you reverse this? What if you have hardware that it's an interface. It receives a packet. It doesn't know how to look anything up. It doesn't know how to just, connect the correct hardware lines and pass it straight through to another port. What if all of that logic is in software? And it's not a matter of, I've received a packet, I am on this VLAN, so I'm going to filter memory and look through this table. It's just like, I got a packet, I don't know what to do with it, so here, CPU, you figure it out. I'm just a dumb interface. You can do that. And if you have a powerful CPU and really efficient software that is built to handle this, then you can do it. It is more unusual to see this in full switches. You can have this in hyperconverged architectures. You can have like a 48 port chassis that doesn't do anything much in hardware. It has multiple CPUs to handle all of this, but it's more unusual. But where you do see this in a local networking environment, you see this inside a hypervisor. Because let's say you're creating 8 virtual machines, and one or two of them need to connect to the outside world. That's fine. But then you have a whole bunch of them that need to have networks amongst the virtual machines, and it's not in actual hardware. You're creating software-defined virtual networks and saying these virtual machines can connect to these virtual networks in order to talk to each other or to the outside world, or maybe some virtual machines are connected to 2 different virtual networks, and here's all the rules for making that happen. That's very software-defined. And so in hyper-converged architectures, a lot of this virtualized networking doesn't actually have to go through physical switching or networking hardware. It stays within the hypervisors because it can, and that way it's faster. So, okay, that's one way of doing software-defined networking. The other place you will often see this is in software-defined wide area networking. The WAN is the internet side counterpart of your LAN. One is the local area network, one is the wide area network. So software-defined WAN means that your internet connection is software-defined. And it's not, here's a hardware interface that is dedicated to routing packets, and then if you have other policies like NAT or firewall, that'll have to get kicked up to the CPU and slow everything down. In SD-WAN, all of that is going through the CPU by design. So you're going to need a more powerful CPU, but this does mean that you can do a few things that are hard or sometimes possibly even impossible using regular hardware connections, at least not without going super expensive. Here's an example of what I mean. Failover, internet failover or load balancing of internet connections. Maybe you have 2 different ISPs, one cable, one DSL. Okay, if you're connecting this in a standard hardware-based routing system, you've got 2 different external addresses. That means you have 2 different networks in your routing table. That also means you're going to have 2 different NAT translation maps, and you'll need some sort of conditions to say when you swap between the 2. And when you swap between the 2, whether for, it's easy enough if one of the connections goes down completely. Okay, it just went down. Now everybody has to switch over to the secondary connection. All right, fine. But that's going to create different NAT translations. That might break some of your existing connections because the remote system was talking to IP address A, and now it has to talk to IP address B. That's going to break their NAT translations. That's going to break their connection maps, and there's nothing you can do about that. But internally, your stations don't necessarily know that anything's happened. They're going out through the internet connection, but it's on a different service. But that can be disruptive. And if you're trying to do something like load balancing, that gets even more complicated because you don't want individual packets to be load balanced. Because if you send 2 packets to Google, and the first one is from IP address A and the second one is from IP address B, your connection's not going to work. Google's just going to say, I'm getting connections from 2 different, IP addresses, and this doesn't make sense to me. So I'm going to reset the connection and tell them to try again. So you can't do load balancing on the individual packet level. And it's not supposed to work that way, again, unless you have very specialized systems like PPP multilink. But for load balancing, you need to balance the connection flows, which means, okay, station A has a connection to Google for, doing searches and everything else. Then they have a second connection to CNN.com, something like that. Okay, that's a different website. and that can go through a separate IP address. But even then, that flow to CNN, maybe there are some ads on that page. Maybe they're using Google Ad services. Does your connection understand that as part of that flow, it should continue using that second connection? Or does it say, oh, it's a connection to Google, so suddenly this connection is going to go over here, and as part of the first connection to the Google website? These are the kinds of things that can be very difficult to implement and will slow down a connection a lot if it's optimized to run in hardware. Is because the rules and the logic for if this then that, that's all being run on a CPU. And if you're oriented towards a hardware switching or hardware routing platform, then it's likely your CPU is not as powerful, and therefore these kinds of things will slow it down. But if you go all the way to the other side of the spectrum, where it's all software defined and you have a big beefy CPU, then you can do things like, I'm going to say, here is a single virtual internet connection, a virtual WAN, a software defined WAN. And I'm going to say that this virtual WAN has a DSL provider connected to it, it has a cable provider connected to it, maybe it has a fiber connector connected to it, maybe it has a mobile like 4G or 5G connection connected to it, and these can all be part of a single virtual WAN link. Now all of your firewall policies to permit traffic goes to a virtual WAN. And suddenly your policies don't really care about, am I using the cable connection's IP address, or am I using the DSL connection's IP address? That's abstracted. To the firewall, it just matters that you're getting a connection that's going to the internet. Okay. The actual interfacing with the hardware, which, yes, it will still require its own NAT translation table. It will still require some of its logic on doing connection flows and everything else. But your firewall policies don't have to worry about that. It's just going to the virtual WAN. The same is true for connections coming inside as well. Because if you've got multiple connections, okay, so you might say, if I receive an inbound connection on port 443, an HTTPS connection on the cable IP address, I want you to forward it to this server. And if you get an inbound connection on, say, the DSL connection, that's a different IP address. Does that also forward? If it does also forward with a separate firewall table, then you also need to take care of the logic saying when it responds, send it out the connection that it came in on instead of out the default connection for that server. Software-defined WAN does the same abstraction there. Your policies are just, if I get an inbound connection on port 443 on my virtual WAN link, then forward it to the server. And when it comes back, same thing. It abstracts the firewall portion of that, and the actual lower level hardware working, there will be another component of software that in the background says, okay, so what connection did this come in on? Make sure it goes out the same connection. What IP address was this? What NAT translation did I have to put in? Just take care of that all in the background. Okay, so software-defined WAN can simplify a lot of things for an administrator, but it's important to note that the complexity hasn't actually gone away. It's been abstracted. To somebody who's just setting up a firewall policy, yeah, it makes it really simple. You've just connected a bunch of, disparate internet connections into a single virtual WAN, and now you just have one set of firewall policies, right? You have firewall policies coming in from the virtual WAN, and you have firewall policies going out through the virtual WAN. But it still has to manage multiple NAT tables. It still has to manage connection flow identification. It still has to manage how do we deal with priority? How do we deal with preference? How do we deal with all these sorts of things? It's just being done behind the scenes. It hasn't removed that complexity. It's just hidden it from you. And if you are a full network administrator, odds are pretty good eventually you're going to have to deal with some of that complexity. So sometimes having software-defined WAN is a benefit because it means you have a more powerful CPU if you're going to be doing a lot of these connections, or you're doing something, say, in a hypervisor where it's being frequently reconfigured and doing all of this stuff. Having the more powerful CPU might definitely be to your benefit. But it's not the be-all and end-all. If you have a relatively stable network and you just want it to run at line speed with a minimum amount of complexity, hardware's your way to go. You can get really good performance as long as you're not doing anything complicated that suddenly requires the CPU to kick in. So, as with everything, it's a balance. It's about what's right for your use case and your environment, but it is something that can be very powerful when implemented in the correct circumstances. So, there you go. A little bit of a discussion on the differences between doing switching and routing in hardware versus software, and the whole software-defined networking as a whole. Hopefully that has been illuminating and a good use of your time. I certainly hope so. If you have thoughts on other things that you would like to hear me talk about or things that you would like to see me demonstrate, feel free to let me know right down there in the comments section. Otherwise, thank you very much for watching. I am your next door net admin, and we will see you next time.